Hello all and welcome to the Basics.Academy channel. So in the last video, we have created this commit reveal contract. We have created the commit reveal contract using which the user can commit the details. The contract creates a hash for that commit and stores that commit inside the commitment structure, wherein inside the structure we have hash is revealed, which is initially set to false, and the deadline after which the commitment will become invalid. Following that, we have a reveal function. Again, for the reveal function, the user passes in the required parameters. The hash is calculated on chain. Then the calculated hash is compared with the hash which has been stored into the commitment. And if those things matches, then we emit an event revealed. And at last, here we have just added a comment which says swap will happen here, but however the exact logic for swap is not added here. The goal here is to learn the commit reveal pattern using Solidity. The smart contract is completed. Today we are going to write the unit test cases for it. So let us do that.
Super Whisper.
Let us begin with the test. Let us begin with the test cases for it.
Oh. Before writing the test code, tell me what are the fever.
Bluetooth mode.
Before writing any tests, what are the three most important cases for commit reveal contract? Happy path, the most dangerous failure case, and one edge case that directly tests the MVP protection guarantee. The happy path involves commit and reveal working as expected. The failure case involves hashes don't match, trying to reveal an already. The failure case involves hashes don't match, trying to reveal an already revealed commitment.
And
Already revealed commitment past deadline, then hash mismatch done, and one edge case that directly tests the MVP protection guarantee. Edge case will be attacker trying to call the same commitment, but his or her message.sender may not be equal to the caller in original commitment, thus guaranteeing
MEV protection. Perfect, you have 5 solid test cases. Let's build them one at a time. Start with the happy part. Write the full Foundry test function setup, calls, and assertions.
Okay, so let us get started with the test cases. I'll open the EIP712 verified test.sol. This will be used as a reference. Then we are going to create. We save this. So this will be. Let me create a file inside test. So we have commit reveal.t.sol. Split right. We are going to copy this because this will remain unchanged. And then here we will import our commit reveal contract. C slash CommitReveal.sol. Then this contract commit reveal test will inherit from Foundry's test contract. At the top level, we are going to define the contract instance for commit reveal. Also, do we need a signer? Yes, we will use address public alias, then address public attacker, then we have our setup function setup. So inside this function public, we are going to create an instance of our commit reveal smart contract. It does not have any constructor. Okay, so our commit reveal state variable is equal to new commit reveal contract. Then okay, so here it is. Our contract is created. Commit token in, token out, token out amount. We will also add the variables at the top level for token in. Address token in is equal to address 1. Then address token out is equal to address 2. After that we have uint 256 amount. Let us say the amount is 100 and uint 256 amount out minimum is equal to 98 until we will use a mapping for tracking nuns. So this will be address user to uint 256 nuts. So this will be user nuts. Your address public alias. So for alias and attacker, inside setup, we will use this public signer. So Alice is equal to bm dot address, and private key will be uint2561. And for attacker, we are going to set the private key to be uint2362. Once we are done with the setup, first test that we are supposed to write is test commit and reveal happy path. Let us do that. Function, this will be public. So test commit and reveal happy path. First, we are going to call our commit function. Let us do that. So when we will be calling commit function, this will emit the committed event. So here we have transfer, test execute, current nuns. We also have another test file which is vault.sol. So here owner, user, non-owner. Yes. I was searching about the prank thing. Owner address is made, the new owner. So what we will do, we will remove this Alice and attacker, and instead we initialize over here make address. This will be Alice and attacker will be make address attacker. We are going to call commit and reveal happy path with Alice's wallet address. So we are done with the setup. After setup, let us check deployment as we have done it over here. Function test deployment. Test deployment public view. So this should assert that CommitReveal dot commit reels dot commitments of say Alice dot length is 0, or else deployment failed. So test deployment is done. Then we have to check our first function, which is commit. We have already defined token in, token out, amount out, men. We also need the deadline. So int 64 deadline will be lob.timestamp plus say after 2 hours. So that will be 3600 seconds into 2. after 2 hours. And the test deployment. So here we have our mapping user nones. Okay. So test commit and reveal happy path. Fame.expect in.expect emit. Okay, we are prank user on all.deposit. So this will expect the committed event. Emit committed with aliases address hash. You will calculate this and then the deadline. Emit committed. We have not expect emit. Dot expect emit. Then we will make the actual transactions, which is commit reveal dot calling the commit function. This commit function takes in, token out, amount out min, and then the nuns will be user nuns of Alice, and then we are going to pass in the netline. Prior to this, him.prank Alice, then you.prank, you not stop it. cm.prank user. After this, we are going to check that commitments, the length of commitments dot length is equal to 1, or KBS commitment key. We will also fetch, let us declare this commitment commitment memory commitment is equal to the commit reveal contract commit reveal contract dot commitments, and we pass in the license address. Once we have the commitment, then we are going to check assert equal commitment commitment. Let us first calculate the hash over here. calculate the hash for testing purposes. Token in, token out, amount, not dot main, nuns. Done. So we have the hash. Commitment dot hash is equal to, let us name this as calculated hash. Dot hash calculated hash or error BB hashes dot which. Then assert equal commitment dot is revealed is equal to false or is revealed don't match. Then at last assert equal commitment dot deadline is equal to the past deadline. The error statement would be deadline don't match. Let us try running the single test case wherein we are able to assert that the commit is working as expected. So I'll go to terminal. First foods format, foods compile, failed declaration commit reveal not found in source CommitReveal.sol. Okay, has to be some spelling mistake. This is a contract. Okay, spelling mistake. Contract is, now it will find commit reveal. For which first format the code and then foods compile. Undeclared identifier committed. Event committed, commit reveal 55.4. Yes, he will also have to define these two events locally, or there's no need to define these two events locally. What we can do is, how are we using this inside emit withdraw? Yes, mirror of events. We copy this, go up, then just view mapping, we paste it. C G Z is. So events are pasted. Let me add the comments. The comment will be similar to this, but limited by commit reveal. So we can use vm.expectable. Now undeclared identifier error will be solved. So it says uint 256 is not implicitly convertible to expected time uint 64. Okay. So we will do 64 explicit conversion. this is done, then wrong argument count for function call one argument grammar expected to assert equal commit reveal.commitments. Yes, commit reveal.commitments. So here we have commitments. Yes, because this commitments is an array. It will not be written directly. However, if we pass in this expects two input arguments. First, the user of the address, and second, the index. Only then it will return the commitment at that index. Since here we are calling directly with alias's address and not passing any index, hence it is seeing invalid argument count. So I don't think this is the right way to check deployment. How can you check deployment? Yeah, just skip this. Then after that, 3680, 3636. No, we have removed that line. Let us format and compile again. So it says to access state variables, use the dot and dot offset suffixes. Got it. So what I'm going to do is I'm going to define this inside the culture. So now it's exist that this declaration shadows an existive declaration. Let it for so declaration shadowing is all sorted. After that, deadline this bin none identify nuns not found. Nuns. It has to be user none. Okay. Showing to 2.6 nuns is equal to nuller nuns of Alice. And after the commit phase, the commit, I will increment user nuns of Alice by 1. Hence this is done. What else is remaining? It says wrong argument count for function call 1. Got it. So this will be, here we will have to pass Alex, 0. And this will not return an array. This will return a commitment. Assert equal. Let me remove this. Commitments of Alice. Let us check if this works. This works. Save. Only local variables are supported to access state variables. Okay, again, the same thing. It brings Okay, in a typo, let us fix this. Commitments. This should be replaced with this. Done. Also, one more thing. Only local variables must be used. Let us do that. Address, token. We have address, token out, then yield 256 amount, then yield 256 amount out min, then yield 64 deadline, as we already have. So here I assign the state variable to this local variables. Okay, now then amount out min, and we have deadline nonsense code. Let us now run it. What it says, only local variables are supported. A different number of components on the left hand side than on the right hand side. Okay, perfect. So even this doesn't work. Let us directly use local variables only, because why we need local variables? Since we are using assembly code to calculate the hash in order to save gas. Plus 2, then mode is 100, mount of minimum is 98, deadline, let me just copy this. So here we have deadline. Now it should work. And also, since this commitments is returning a structure, and this structure, no, it is not. So it says wrong argument call, one argument given, we will pass in 0 because Alice's first commitment is pushed at index 0. So from index 0, we are going to get bytes 32 hash, bool is revealed, and at last you end 64 deadline. Now let me remove this commitment. Now it should work. Okay, shadows and execute declaration. The table be like 9 numbers 70, right? Install tokening. Get this shadows existing declaration. Okay, so I use this as underscore deadline. Here we will check which deadline will be. Okay, which deadline underscore deadline with the actual deadline. Also, here it will be local variable token in, token out, amount out, lag, nuts. Now everything should compile without any warnings. Still we have identifier already declared, unit 64 deadline. Already declared here solely nuns underscore deadline. It is already declared. Okay, let me change this to commit deadline. So I have commit deadline. successful with warnings, unused local variable. Okay, so we are not using this. Let me check commit reveal contract. Inside commit reveal, are we not using deadline into the commitment? Stock commands. No, we are not. No, deadline is not used inside the commitment. So this deadline unused, let me remove this variable. Now let us compile. Done. Or let us run the test case. So we will run the test case for commit reveal. Okay, committed param mismatch, add commitment dash, expected this, got this, encountered one failing testing test CommitReveal.t.sol. So one test is failing, the test is failing at committed param mismatch at commitment hash. One failed, skipped 0. Committed param mismatch at commitment hash. So this is calculated hash. Then we pass it token in, token out, amount out main. Then we use nuns. We just use nuns here. And the deadline. Calculating token in, token out, amount out in nuns. Calculated hash. Then we check hash caches do not match. Ran one test for test slash CommitReveal.t.sol, CommitReveal test, expected is this, got is this. But from where exactly it is faded? This is our assembly code. Topril, Tokeno, Ryan, Tomato, none. Update free memory pointer, calculated hash, schooled. This is this, calculated hash, seal the code, you not expecting it. With committed. Here is to pass it off. First test case. And running this, it is failing with the hash calculation logic is copied as it is from commit reveal contract. Okay.
The bug is in your test side assembly. When you use caller in the test, it returns the test contract address, not Alice. But the CommitReveal contract computes the hash with Alice as msg.sender via vn.track. How would you fix the hash computation in test to use Alice's address explicitly?
How could you fix the hash computation in your test to use? So here we have caller. So instead of caller, but when we are calling commit reveals commit, so inside that the caller will be a commit reveal test contract and not Alice. Oh no, we are using prank Alice. Here we have to use Alice. Think this should fail. What it is saying, how would you fix the hash computation in your test to use Alice's address instead of caller? And just try running it. Use the dot slot and dot offset suffixes. Sim out it as state variables in assembly solid. So true result var 3. That's because state variables are not to storage slot when possible. Third variables have the following boolean 1 byte, uint 8 1 byte. Given that storage slot is 32 bytes, all three of them can fit in the first slot. Okay. Now because they are packed in the same slot, they cannot have the same offset, which is reflected by the value slot 0 itself, where byte 0 is var1 boolean root, byte 1 is var2, and byte 2 is var3. To get the third variable, you want 1 byte from storage slot starting at offset var3.offset. Okay, first load var3, get the value at this, then shift the value by var3 offset into 8 bits to the right. Then store the result for return. Okay. So in our case, Alice, this is slot 0. This is slot 1. So Alice's address is stored at slot 1. Who can we access that? Get slots. Key slot 1. Yes, lower. But it is lower as so we are going to use Alice. Let's load. Then what is bad here? Var3. Okay, so Alice dot slot. So the Alice dot slot. Let us try running this. Okay, compilation is successful. Now let us try running the test cases. Now it has passed. So the issue was we were passing in the caller, hence the calculated hash was different from the one which was being calculated inside the smart contract. Now inside the smart contract, the caller was Alice, and here the caller was not Alice. Hence the calculated hash was not matching with the hash from within the contract. How would you fix that? It is fixed by using a load alice.slot, as Alice is a state variable inside the test contract.
Slode of Alice.slot works, but it's fragile. In tests, gas doesn't matter, only correctness. Why not just use KCAC 256 of abi.encode directly in the test passing Alice explicitly? What would that look like?
Makes sense. I used assembly. With a bow of saving gas. However, I forgot that. However, it skipped my mind that tests are not run on VJave. Let me use abi.encode instead. That could be much simpler.
Exactly. Fix the hash computation using abi.encode with Alice explicitly. Then share the updated text.
Okay, talk about amount. Then we have amount.main handles. This will be given to get check to fix. So assembly, thank you, but you are not needed. KM's variables. Done. Done. Here it is.
Teen and correct. One small thing, vm.pranked only pranks the single call, so vm.stopPranked after it is unnecessary. vm.stopPrank pairs with vm.startPrank. Which one should you use here? And does the test pass now?
I should use vm.prank and the tests are passing now.
Perfect. Now add the reveal portion to the same happy path test. What calls do you make? What event do you expect? And what do you assert after the reveal executes?
Now we are going to write the reveal part. So for reveal part, again, we will expect the revealed event. Expect the revealed event alias and commitment hash is same as that of the calculated hash. Then aim.try if.break alias, then we will call the reveal function. When we are calling reveal function token in, token out, amount out, main none's index. Here the index will be 0. After that, it will check this. The after that, it will load the commitment from storage index 0, which is this. But this thing will be loaded into the contract. Deadline is not passed, not already revealed. It will again calculate the hash. After calculating the hash, it will check if both the hashes are equal. If yes, then the is reveal will be set to true and revealed message.send the calculated hash. So we are going to again, after revealing, fetch the same commitment for Alice, and in this case is revealed will be true. Be it true, I think we can safely remove this because you already defined hash is revealed above. So let's remove this. Now let me run this test case again. Done. Expect the revealed event. Here is the reveal part.
Gene and correct. Does the full happy path test pass with both commit and reveal?
Yes.
Now write test reveal hash mismatch. What do you change in the reveal call to trigger the hash mismatch revert, and how do you assert it in Foundry?
Test reveal hash mismatch. So we have function test reveal hash mismatch public. Now again for this function, first we will have to commit. So I use the same code. The commit part. Let me create a helper function. So function underscore commit. Helper function to create a valid commit. So first we are going to create a commit. Test reveal hash mismatch revert and audio assert that in Foundry. So when we call reveal, that time simple. The event will not be emitted because this is going to be emitted hash mismatch. Hash mismatch, so revert BM expect keyword expect keyword latest Got it. Expect revert. So our custom error is, this is our contract commit reveal. Commit reveal dot hash mismatch dot theater. It has to be selected. Yes. Dot save. Dot selector token in amount count. You will pass in this as 95. So commit was created with amount out min equal to 98 and reveal is being called with amount out min equal to 95. Hence the hash will mismatch and the transaction will be reverted with hash mismatch. Declared identifier hash is revealed. Got it. One undeclared identifier calculated hash. Undeclared identifier nuns. Declared identifier nuns. Commit internal introduce backpack navis. So I'm just redefining nuns at this at here, and we will be passing nuns as a variable to the commit function. So nuns is here. Quickly copy this here. Done. Then we have this internal. This will returns bytes 32, and it will return the calculate hash. Cheatcode hash. So we have bytes 32 calculator hash equal to command. Here also bytes to be taken. Compiling wrong argument call, okay, what it thinks, passing the lens shall also once the lens now format and compile done, none the test cases done. Test reveal hash mismatch. Done. Created a helper commit function which will be used across tests for committing purposes.
Excellent key, well commented.
Yes, it
And
does.
extracting commit into a helper is good test design. Does it pass? Now write test reveal already revealed. What sequence of calls do you need to set up the scenario? And what do you assert?
The sequence of calls will be commit, then revealed, and again called revealed. And when revealed will be called again, that time I will assert expect revert with the selector of already revealed custom error which we have defined in the contract.
Exactly right. Commit reveal again, expect revert with already revealed selector. Now write the code.
So here we have public first get hold of the nuns, then call commit. After calling commit, call the reveal part. Reveal part should work as expected. Reveal part should work is expected. Here we have calculated hash. Then after this, calling reveal again must revert. Commit dv dot already dot selector real codes. Now let us compile, format, compile, and run the test cases. Done on the test cases. Done. The tests also pass.
Perfect. Now write test reveal PassedDeadline. What Foundry cheat code do? You need to simulate time passing beyond the deadline.
So, first add like then this will be public. Here our first commit. After committing VM.advance Foundry cheat code to pass timestamp. VM.warp set the timestamp to 1 hour after the Unix. Okay, VM.warp. This is it. Fast forward time relatively used to increase the current by a specific number of seconds. Okay, warp sets the timestamp to 1 hour after the Linux epoch. VM.skip. Then advance time to 3 hours. Dot skip. So 3600 into 3 is 1,08,000 seconds. So loud Q6 was 10,800 seconds all. After this, we will call the reveal part. Calling must revert with get a revealed, and this must revert with past deadline. So first is nuns, then commit, then advance time to 3 hours, then calling reveal must revert with past deadline. Does format compile. Okay, VM.skip is not found or not. Then we don't have VM.skip. Let us check the documentation. Cheatcodes environment. Okay, it is VM.war. Sets block.timestamp to the specified value. See also skip forward in time. Okay, so instead of, let us use just skip. Instead of VM.skip, I will use only skip. So now let us try compiling this. It is compiled. Calculated hash is not used. Let us remove this. Now let me call format and compile done. All the test cases done. Done. The tests are passive. The Foundry cheat code is skip with number of seconds.
Clean and correct. Now the most important test, the MEV protection guarantee. What exactly does the attacker attempt, and what do you assert?
Function in this so Alice has created a commitment. Alice has already created a commitment. Now what happens? The attacker tries to call MEV.bank attacker. The attacker tries to call the reveal part. The attacker tries to call the reveal part by passing in the index 0. Now this index 0 is of stores the commitment of Alice. But exactly what will happen is, and the attacker will call this, here the hash will mismatch because the commitment, when the commitment was created, caller was Alice. And now when reveal is being called, caller is the attacker's address. So this hash is called calculated hash is not going to match with the commitment hash. Then we are going to get this hash mismatch error. So we'll capture that. Most revert with hash mismatch. Key. What exactly does the attacker attempt and what do you assert? And going back to the test case, here it is.
Perfect. Notice what makes this test elegant. The attacker passes identical parameters, but msg.sender is different, and that single difference causes hash mismatch. The address binding is the entire defense. Do all 5 tests pass together with fourth test?
Error expected panic array out of bounds. Fifth one is failing. Commit and reveal is passing. Already revealed is passing. Reveal hash mismatch. Reveal past deadline. Array out of bounds. Why? So here you're calling else it nuns. Create commitment. CommitReveal.hash mismatch.selector attacker. Then call the reveal with nuns 0. Strange. Last test is really with
Think about this carefully. The error is array out of bounds, meaning commitments attacker index 0 doesn't exist. The attacker never committed. Which line in reveal triggers this panic before it even reaches the hash check?
got it. Line 56. So it means the attacker can never break through our system. The attacker can never break through, so it means the attacker can never break through our system, as it will always panic. Since attacker doesn't have any commitments.
Correct, but a panic is not the same as a controlled revert. Panics consume all gas and give to a UX. What explicit check should you add to reveal before accessing the commitments array to guard against this cleanly with a custom error?
What check should you add to reveal before accessing commitments message of sender of index? Before accessing, if commitments of message dot sender dot length is greater than 0, this must be added.
True, but the condition is inverted. You are to revert when the array is empty. What is the correct condition and what custom error would you revert with?
The condition will be if not commitments of message dot sender what length then they were no commitments. Derogate the definition of custom error at the top.
Perfect. But what if the attacker passes index 5 when the array only has one entry? The length check passes but you still panic? How would you make the bounds check cover this case too?
Right. But there's one more edge case with this check. What if the attacker passes index 5 but the victim only has one commitment at index 0? But this will check the commitments of the attacker near the victim. Same. If the index is greater than the length, then also mute. If not commitments of message sender dot length, let us see the message commitment length is equal to this. If not commitment length, or index greater than commitment length. Greater than. Alright.
Almost, but there's an off by 1 error. If length is 1, the only valid index is 0. But index greater than length allows index 1 through. What should the comparison be? Correct. Note that index greater than or equal to commitment length is more idiomatic than avoids the subtraction entirely. Both work here since the zero check comes first. Now update your attacker test to expect no commitments instead of hash mismatch and confirm all 5 pass.
If index is greater than equal to commitment length, 0, commitment length is 0. Forge format, forge compile, done, run the test cases. Yes, all the test cases are passing.
All 5 passing, excellent work. Let's do a quick knowledge check before we close the session. Question 1. In a sandwich attack, the victim's transaction still executes, it doesn't fail. So why does the victim lose money?
The victim lose money because the attacker has inflated the token X price, which impacts the victim's total swap value.
Correct. Question 2. Why is abi.encode safer than abi.encode impact for computing commitment hashes?
Because it pads each value to 32 bytes, which makes abi.encode hash collision resistant.
Correct. Question 3. In your reveal function, why must commitment.isRevealed equal true happen before the swap interaction, not after?
Because there may be chances of re-entrancy.
Correct. Question 4. In your ULSMD hash computation, why do you use caller instead of msg.sender, and why does this matter?
In assembly, we use caller to get hold of a message.sender value. We cannot use message.sender directly in assembly. This matters because the hash computation is to be done using the caller of the transaction.
Correct. Final question and the hardest one. The commit review pattern protects against front running during the commit phase, but during the reveal phase, your actual swap parameters become visible in the mempool. What residual MEV risk still exists, and how would you mitigate it?
The CUH-based MEV risk is that the attacker can still front run the swap, trying to inflate the price, and leading to loss of tokens received from the victim. The mitigation can be done by keeping the deadline within 10 to 15 seconds, that is hitting a new block creation for Ethereum.
Good instinct but a short deadline doesn't prevent same block front running. The attacker can still see your reveal in the mempool and front run the swap within the same block. The real mitigation is at the infrastructure layer. Have you heard of flashbots or private mempools? And what do you think they do?
Private mempools, I'm guessing here, does not be or swap data, and flashbots maybe execute your transaction as soon as it enters the mempool without giving time for the attacker to reorder the transactions. Okay.
Strong session overall. Your 1 week area is flashbots and private mempool infrastructure. Read the flashbots tasks before next session. Well done today.
Okay, so private mempools route your transaction directly to a block builder without it ever touching the public mempool. The attacker never sees it, so front running is impossible. Flashbirds specifically lets you submit bundles, a set of transactions that must be executed atomically in a specific order within a block. Your commit and reveal can be bundled together into a single block, eliminating the window between the two phases entirely. So the strongest mitigation is submit your reveal transaction through a private mempool like Flashbots protect, so it's never visible to any MEV bots. Okay, section create weak areas to revisit Flashbots architecture and private mempool infrastructure. Read the Flashbots talk before next session. Resources for next session, Flashbots docs. Start with MEV and front running and Flashbots product. Okay, so this marks the completion of MEV risk and mitigation, wherein we created a commit reveal contract. Then we added Foundry test cases to ensure that whatever we have written is working as expected. And the final MEV mitigation approach is to use private mempools and flashbots. So in the next video, we are going to look into flashbots and private mempools. If you have learned something valuable today, please do like, share and subscribe. Thank you.